What is up, guys? So today we are doing electrostatics, and this is a really awesome part of physics that I really have a heart for. And the thing is, with electrostatics, let's first start with our goal in electrodynamics as a whole. So we'll have these source charges right here, and they'll be like Q, right? And then we have our test charge anywhere else, okay? The whole goal about electrodynamics is to find what is the effect that these have on Q. What is the force that these source charges have on Q, and how does it affect Q? What is happening to Q, the test charge? So a version of this problem is where the source charges are stationary, okay? And this whole definition of stationary source charges, the Q charge can do whatever it wants. It can move, it can come closer, it's free to do whatever it wants, but our source charges are stationary. This whole concept we call electrostatics. So we can look at problems where our source charges are stationary. And this is great. So first result we have for electrostatics, and basically that we'll be using a lot, like that in the Biot-Savart law. So we have our old man Coulomb, who said the following. Coulomb said that the force that Q has on Q is 1/4 pi epsilon naught. This is the permittivity of free space, and then Q, the charge on the source charge, and your test charge at the separation vector, and the magnitude of the separation vector squared. So this looks familiar to your school definition. And I think in first year, many of you will have been working with a different version of this. The only thing that might be strange is this thing here. So let me just quickly help you and tell you that this is actually just a vector that says that if this is our source charge and this is our point charge, well, we define this as that vector and this is this vector. And then the separation of these two charges is defined as the separation vector, and the separation vector will be something like R minus. Okay, so with this we can actually elaborate this statement in different ways and say like, well, okay, so Coulomb's law can actually look a lot different. So it can look like this as well. It can, like, everything stays the same, but you just rewrite this as follows. So this is another way you can interpret Coulomb's law, but normally we'll be working with this one. It's the prettier one, and they both actually mean the same thing, so no problem. At least you know this is just a separation vector. Okay, so let's look at the application of Coulomb's law. So first thing you need to know is that, well, Coulomb's law is really great, but it only, it's defined for one effect of a source charge over the Q charge, right? So we have the effect of one of the source charges. Well, we're in luck because superposition is possible. All right, well, superposition occurs for Coulomb's law. So what this means is if we have a bunch of source charges and we have our point charge Q, well, this is so easy as to say that the force that these two have on each other, and the force that these two have on each other, they can all be worked out individually. And once you have all of them, well, the sum of these, that's not the sum of these forces on Q will be the total force on Q, which is awesome. So you can literally go and be like, oh, well, the force of 1 over Q plus the force of 2 over Q plus that will give you the total force on Q. And that is great. That is good news for us. So thankfully, we can do a lot of complex problems with just Coulomb's law and the superposition principle. And an example of this would be, and this is a simple one, we'll later look at difficult ones, we'll have the following. So let's say we have, I'm using the circle as a reference, but basically what we're going to have is like these guys all directly across from each other. These are all source charges. And then we have one Q charge in the middle. Now, all these charges are charged Q, okay? And let's say positive and positive repel each other. This is a natural law. Okay, so Q experiences a repulsive force from this one. Okay, and it also experiences a repulsive force from this one. Okay, and so we continue, because it's going to be the same everywhere. And then we use just the fact that the superposition principle accounts, and we'll see that the total force on Q is just 0 Newton, which is great. And that we just use by basic natural laws in electrostatics, and also the fact that superposition principle accounts in Coulomb's law. Next, we'll look at what an electric field is and how it correlates with Coulomb's law.